Hello and welcome to Fun with Lists. A list of items provides an excellent way to explore a new topic or dig deeper into something interesting. Online and in R packages, lists are available on virtually any topic imaginable. Looking at these lists in R-Instat enables you to delve deeper and manipulate them to reveal and extract information that interests you. Once you discover a topic through a list, it's easy to follow up and delve deeper using Wikipedia, Google searches, or through more lists. There's a fascinating amount of information at your fingertips today, so explore. In this video, we examine a few of the many lists that are available, mainly from the R-Corpora package. We start with animals. From the animal options available, we choose dinosaurs. Wow, that's quite the list. There seem to be 1,449 dinosaurs on it, some of which have very long names. Once the data's there, scroll through and think about what you want to do with each list. What is of particular interest to you? Do you want to add value or just clarify the data? We choose to examine the length of the dinosaurs' names. They are in a text or character type column. That's indicated by the C with the name of the column. We use prepare, column, text, transform, length to get the number of letters in each name. We complete the dialog by adding list as the column to transform and renaming it length. Then we click OK. Here it is. Though our next task is to sort the column by length, we first use prepare, data frame, row numbers and names to copy the row number that's on the left into a variable with the current order of the data. We then right-click from within the length row to provide another menu with items we use a lot. Choose Sort to see the names in their length order. We sort in descending order and discover dinosaur number 852's name has 23 letters. It's a Micropachycephalosaurus and is the only one with more than 20 letters in its name. There are many other animal lists if you prefer, but now we look at food. Start with bread, then fruits, followed by vegetables. We could go on. Did you know, for example, that there are at least 189 different herbs, 528 teas, and 1,000 types of apple? But we digress. Our three open lists would be easier to examine if they were together in one sheet. That's an example of reshaping the data. So use prepare, data reshape, and then append. First, we add all three data frames. Then we call the ID column type and the new data frame food. Now we use the right-click menu again, this time to make the food variable into a factor or category column. Once it's a factor, we can use levels and labels to see how many instances of each type of food we have. If you're a crossword fan or just into language, the word clue lists are really interesting. We're going to look at those for four-letter words. Our list is organized alphabetically. Here are the four clues or synonyms for also, in addition, besides, as well, and plus. Overall, we have 4,005 clues. But it isn't obvious how many four-letter words these relate to. Let's find out. We put the clues across rather than down. Make the column called variable 2 into a factor. Then use prepare factor, count in factor to give the clue number for each word. Call the new column clue. Then reshape the data again, this time using prepare, data reshape, and unstack. Use the clue variable for unstacking. Unstack the list column and carry with it variable 2. Add the prefix clue. This is sometimes called pivot wider, though we still like the idea of unstacking. Next, right-click at the top to delete the first row, which is just a sort of title. Now it's clear this list has 1,160 four-letter words and up to 7 clues for each word. Where values are missing, they're shown as NA, which is usually fine. But here the list would be clearer if they were blank. We use prepare, data frame, replace values to make this the case. That looks much better. Scrolling down shows that draw is the first word with 7 clues. Within those 7 clues, there are 4 or 5 different meanings for the word. We now move on to science. Let's look at planets first. That's a surprise. I thought there were 8 planets, but there are 13 listed. I didn't know about dwarf planets. I see some dwarf planets even have moons too. The moon variable looks complicated. It would be good to split it into moon by moon. Let's use prepare, column text, split. We divide by the variable list moons, select maximum number of components, and add the prefix moon to the new columns. As everyone knows, Earth has 1 moon, and now we can clearly see that Mars has 2. Meanwhile, Jupiter has 63 moons, which is why we have 67 variables in total. A list of minor planets is also available. Let's go back to New Data Frame and have a look at that. This lists the first 1,000 minor planets. I wonder if the order of the list has any purpose. Maybe we can go somewhere else to find out. Let's do a quick search on Wikipedia. Here's a list of the first 1,000 minor planets on Wikipedia, and it looks like it's in the same order as our list. But the Wikipedia list has more information. We can see that both lists are arranged in ascending order by date of discovery. I wonder where this list came from. If we scroll to the bottom of the Wikipedia page, we can see that the data is available from the Minor Planet Center, and there's a link. Mathematics has its own section. We start with the first 1,000 Fibonacci numbers. To make the Fibonacci sequence, you just add the last 2 numbers to get the next one. So they start quite innocently. 1 and 1 is 2. 1 and 2 is 3. Then 2 and 3 is 5. But did you realize how large they can get? The 21st Fibonacci number is over 10,000. Let's compare with the first 1,000 prime numbers. It says 1,000, but actually gives a bonus of an extra 10 primes. So we've got 1,010 rows. The 1,000th prime number is just 7,919, so much less than the 21st Fibonacci number. The lists also give the first 1,000 primes in binary. That's a bit different. It would be nice to see the 2 prime lists side by side. Before joining the datasets, we need to add a row column to each one. This is a great opportunity to use the OK Keep button. This keeps the window open for me, so I can simply change the data frame and add one to primes as well. Now we're ready to join our data frames. We go to Prepare, Data Reshape, Join Merge. We add the primes binary as the second data frame, and then use Join Options to define our newly added row as the key column. Then we use column selection to ensure that only the list column is added from the primes binary data frame. Here's our new merged data set, with the primes and the binary primes side by side and easy to compare. Of course, in binary, every number in the list ends in a 1, because all prime numbers are odd. Let's look in more detail at 11. 11 is 1, 8, no 4s, 1, 2, and 1, 1. So in binary, 11 is 1, 0, 1, 1. If you'd like to know more about binary, a great video is called How to Convert Decimal to Binary by Number Systems. You can watch it on YouTube. I wonder what it did with those bonus 10 rows. Oh, that's sensible. They're just missing for the binary column. With any of these lists, it's easy to look for more information, or maybe just a longer list. Let's look up 50 million primes. We quickly find this very nice site with easy to download lists. Let's look at the first million primes. We download it, and then I'll unzip it. Once you've unzipped it, use the open file icon to bring it into R-Instat. Browse to the file location, and here's an overview of it. If you're happy with how it looks, click OK to open the data. They come sort of across rather than just down. That's quite nice to look at. I noticed some twin primes. For example, 3 and 5, 5 and 7. That's as close as primes can get. Oh, and 17 and 19, 29 and 31, and 41 and 43, and so on. I also notice, starting on the second row, gaps of 6 are quite common. 23 and 29, 31 and 37, and 47 and 53. I wonder what happens when the numbers get bigger. Let's go to the end. Now the prime numbers are quite big. But look, the last two have a gap of 6, and so do the two before. This shape of data is great to look at, but not very convenient when you want to do something. So let's stretch it out. Use Prepare, Data Reshape, and Stack again. We add all our variables into columns to be stacked, and type primes into values too. Then click OK. Now our column of primes is 1,000,000 long. Next, let's get a column of differences. An easy way uses Prepare, Column Numeric, and Transform again. Primes is our column to be transformed, and we want the difference. Click OK. In the column of differences, we now see the 2s and the 6s, just as we discussed. We digress just for a minute to show you another way to get the column of differences. Often, software gives you alternatives, and the transform dialog means you don't have to bother with the R-Instat's more general calculator. But here it is on the Prepare menu. And it looks quite innocent, doesn't it? Almost like a calculator on your mobile phone, and you can use it like that. 154 times 14 equals 2,156. But it's much more powerful than a calculator on a phone, because it's mainly a column calculator. It also has a collection of extended keyboards, so you can do many transformations of your data. Here we need the transform keyboard. We press the difference key. That does look a bit scary, perhaps. We're actually constructing an R command. We persevere and include the primes column. Now click the try button. It seems to work. And we get the same results as before. Maybe that wasn't so hard. It's easy to get frequencies if we make primes 1 into a factor column. Then we use the right-click menu again to open the Levels and Labels dialog. It's interesting that there are 86,000 gaps of size 2. That's twin primes, so about 1 in 12 is a twin prime. But there are many more gaps of 6, and gaps of 12 are also quite common. Earlier, we looked at the first 1,000 primes as binary numbers. Now we do this for the first 1,000,000 primes. We use the calculator again. This time we choose the integer keyboard and click the binary key. Add the primes variable, try, and click OK. Notice, of course, that all the binary numbers end with 1 because they're all odd numbers. While we're playing with the calculator, let's also show the numbers to base 16. That's hexadecimal. We first reset the calculator, go back to integer keyboard, and choose hex. Put the primes variable in and click OK. Here's our column of hexadecimals. There's so much to investigate, even just using the 50 million primes site. What happens with even larger primes? How would you investigate? Are gaps of 6 always the most frequent? Perhaps the relative frequency of twin primes will overtake, or perhaps they'll become progressively rarer. But here's another set of lists to investigate. Return to the words section, and this time to literature and Shakespeare's sonnets. He wrote 154 sonnets, so it isn't a surprise to see that we have 154 rows of data. A sonnet is a special type of poem with 14 lines. Here the data goes sonnet by sonnet, and they might be easier to read if they were arranged line by line. Let's do that. We first split the data so that each time there's a double quote followed by a comma, then it splits. This has the interesting feature that we want to use the quote symbol to split by, when usually it starts and ends a string. This is a simple regular expression, and we give it like this: backslash, quote, then comma. Then we choose the maximum number of components and click OK. Great, it worked and produced 14 variables with 1 for each line. It would be better if they were stacked, but we'll do some housekeeping first. You can see that line 1 has the C and open bracket at the start, while the last variable has an extra closing quote and a bracket. Let's get rid of these quickly. To do this, we go to Prepare, Column Text, and Transform. Our variable to transform is split, our start value is 3, and our end value -1. We change the column name to split because we want to replace the existing column, not add a new variable. As you can see, our transformation is complete. The C and the bracket have been removed from the first line. We now repeat the process for the last sentence to remove the quote and the bracket. Split 13 is our column, start value 1, end value -3. And once again, the column name should match the original variable name. Now that we've successfully removed the quote and bracket from the end as well, let's stack the data so the poems are all back into a single variable. We return to the Prepare menu, Data Reshape, and Stack dialog. We include all of the split columns and add them to the columns to stack. We choose to carry the list number, and we call the values line. We decide to drop the prefix split so that we just keep the number. Then we click OK. That's much clearer. we can see that there are 2,156 lines of these poems. That's 154 sonnets times 14 lines for each of them. Some people say that sonnet 18 is one of the best, so let's filter to look at that one. First, make the first variable into a factor. Then use right-click to open the filter dialog. Next, we define a new filter. We choose to filter by list number, and here are all the levels available to filter by. Click on 18, add the condition, and return. Now we click OK to apply the filter to our dataset. Here it is. Aren't lists sometimes surprising? They include this short poem written over 400 years ago that compares the variability of climate to an individual's changing personality. We hope you agree that lists can be fun. And many more lists are available if Shakespeare isn't your favourite. For literature, even the Gutenberg Library has an R package. This lists over 50,000 classic books, all of which can be freely downloaded and enjoyed. And finally, if all you know about statistics is the quote about lies, damned lies, and statistics, then there are many more here from the Stats Quotes package. My favourite is number 79. I always find that statistics are hard to swallow and impossible to digest. The only one I can remember is that if all the people who go to sleep in church were laid end to end, they would be a lot more comfortable.